Welcome to a video series on MAC 1105 College Algebra. In this series, we'll be going through the guided notes for this class. This will be the first video in that series, going over section 2.1, Graphs and Graphing Utilities. So because this isn't the first course in algebra, I will presume some knowledge about how graphs and equations work, but I'll also try to make this self-contained as much as I can. The first thing we need to recognize is that two variables have been defined in the problem, a y variable here and an x variable. When we've solved for a variable, like this y is solved for, we can consider this to be our input, our x's are our inputs, and this y is kind of an output after we do something to x. So for the first y value that we're going to figure out, we want to plug in minus 3. Now y is equal to x squared plus 1, so we put the minus 3 in where x goes. Minus 3 squared is 9 plus 1 is 10. We continue that process for each input. Negative 2 squared is 4, plus 1 is 5, and so on. Once we calculate all of these different y values, what we have are actually coordinates. We have a set of points, x comma y here, right? Negative 3 comma 10. And we're going to be plotting those points first along our x-axis and our y-axis by plotting the x value and y value respectively. So we find our x value, that's minus 3. We find our y value, that's 10. And we want to plot at this height, 10, and this left or right kind of location, minus 3. So where are those both true? Right here, this would be the point, minus 3, 10. Minus 2, 5 would be here, and so on. Once we get this collection of points plotted, we want to connect them as smoothly as we can with a line. So, and we also want to respect the trends that we can see on the graph, namely that this is going to keep on going and keep on getting up, even though it's off the graph at minus 4. There's still something happening up here. We just can't see it, and we're not going to plot it, but we should be aware that it's there. So we want to try to smooth that out. We don't want to make it too blocky, because we can see that the slope is changing. Here it's going down by 5 units, here only by 3, here only by 1, and then it definitely changes and starts going up instead. So when the slope is changing, you really want to smooth out your line as you draw it. But then that would be it. This would be our graph. Now let's consider how we could graph this equation to do it not by hand. Let's use some technology to help us out. For example, you might want to use a graphing calculator. I have an emulator of a graphing calculator. To plot that, you could go to y equals, and we could type in the equation as seen here. X squared, leave our exponent, and then plus 1, and then look at the graph. It would give us these values. We could also go second table, and scrolling up or down, we could get a set of points for these integer values. The integers will be the standard inputs for x, although, if you want to get fancy with it, you can change those in the table properties, or table set here. But at the very least, we can confirm that our graph looks appropriate. Another piece of technology you could use if you don't have such a graphing calculator and you do have the internet available is you can use Desmos. So here on Desmos, I would type the equation, including the y, and would also graph the way that we had it seen on the graph we did by hand and on the graphing calculator. Now, I won't be using those two utilities to graph every single one of these functions, but I might graph a selection of them if I think the graphs are particularly interesting, or if I want to show you some new feature on either the graphing calculator or Desmos. In the meantime, let's go on to this slightly simpler function. Again, it's the same procedure. You take a look at what your x value is in the table. Y is going to be equal to that value put in place of x, in this case minus 1. And of course, minus 3 minus 1 is minus 4, and we continue in this fashion. Once we have this collection of points, we could plot them. So minus 3, 4, that's minus 3 and minus 4 here, and so on. And you probably notice that all of these points are collinear. They start to trace out a line. If we connect those dots and extend that line, and this is important, you must extend the pattern even beyond what's on the table, then we get the following graph. Often we'll put some little arrows on the end to show that this really does continue on indefinitely. Just like before, we could start to notice some geometric properties. Here we could see that the function was even, it's symmetric around the y-axis, and that explains the repetition in the numbers. Here we can start to note the properties of lines, like the fact that it has a y-intercept of minus 1, the fact that it has a slope of 1, it goes over 1 and up one each time. But we'll talk more about the graphing of lines and the forms of lines later. Meantime, let's move on to the next one. Here we have two interesting lines. They're probably kind of boring, but I think that they're very important to consider. We've got the line y equals 6 and the line x equals 4. Now, y equals minus 6. Well, here's minus 6 on the y-axis, but actually not just that point, which is 0 minus 6. Here's the point 4 minus 6, or negative 7 minus 6. No mention is made of x in this equation. Only y is in this equation. And the only stipulation we have about y is that it must be minus 6. So any one of these points that I've plotted here must be on the line. And we can see that even though this is the y coordinate, which is this vertical axis, it's actually constantly minus 6, and constant regions of constant values of y are tracing out horizontal lines. So there's a little bit of a switch there from what you might expect, but if you just think, well, my y value has to be minus 6 and plot some points, you'll see that that actually has to be the case. And likewise for minus 4, and likewise for x is equal to 4, we're going to have to, well, here's 4 on the x-axis, but all of these values up and down, every value here, and all the points in between these points, have an x component, which is positive 4. Y is allowed to vary, and that makes it a vertical line, but the x is constantly 4, and that makes it this vertical line. Connecting those dots, we get this following graph. And I just want to reflect on this idea that they have this intersection here at this point. And at that point, your x value is equal to 4, and your y value is minus 6. So where do the lines y equal minus 6 and x equals 4 intersect? They intersect precisely at the point 4 minus 6. Here we have an absolute value to graph. Absolute values will take something and make it positive if it was a negative, or if it was 0 or a positive number, the absolute value will leave it the same. And this is because absolute value indicates a number's distance from 0, where distance is considered a positive quantity, or at least a non-negative quantity. You can be of distance 0 from something. So if I, for example, take 3 and multiply it by the absolute value of minus 3, the absolute value of minus 3 is just positive 3. And so this product is 9. If we continue in this fashion, we get the following products, which evaluate as such. And plotting these points, we get the following shape. Now we should notice that from 0 onward, this is actually has the same slope between all these points. This is a straight line. So it's linear, at least on that part, but on the other side, it does something different. It bends at a sharp angle, and we get this other line on that side. So this is a characteristic sharp-angled V shape composed of these two rays that you'll see almost always when you graph some kind of linear absolute value like this. So let me show you how to get that on the calculator. On my calculator, it's found under math, over under number, and then we have abs. So we want absolute value of x, and oops, I forgot to put a 3 in front of there, so let me insert a 3. And it should understand that adjacency means multiplication, but just to be on the safe side, I'll say that is 3 times the absolute value of x. Take a look at this graph. You can see something similar to our graph here. On Desmos, you can either type abs of x, put that in parentheses, and that will indicate your absolute value. Or if you use the vertical bars, it will also recognize that as absolute value. So either of those two inputs will be understood by Desmos. Okay, let's move on to the next one. Here we have a more complicated but still linear absolute value. That means just multiplying by constants and adding constants. Nothing else is going on here. No squares, nothing like that. So let's take a look at that. We want to evaluate this at each position. For example, this is 5 times the absolute value of minus 3 plus 3. Make sure you're respecting the order of operations here. So that's 15 plus 3 is 18. So we'll continue as such and then try to connect the dots. Once we get these points evaluated, it's 13, 8, and so on. So if we notice we have some 18s, that's well off the edge of the map. Same with the 13s. Well, let's just plot what we know, and let's try to extend our understanding of the previous graph to this one here. So for example, really the only things going to be on the map are going to be these, We'd need a larger and more extended graph if we wanted to hit some of these other points. But as such, all we can really hit is 0, 3, minus 1, 8, minus 1, 8, and positive 1, 8. So let's connect that V shape together. And this would be the best we could do to graph this graph, 5 absolute value of x plus 3, onto this 10 by 10 window. When we graph on Desmos, we have the ability to sort of leave and see a wider window if we want with some handy tools. And then we could see, in fact, right at -2, we do have the prescribed values, and -3 as well. We do get the same values that we worked out on the table. On the graphing calculator, let's get our function edited here. Once we get that function input correctly, we could check the graph. It does look like our graph in this window. The window that we have right here is -10 to 10 on both axes. We could control that graph exactly, and if we expanded that graph, we could see, a larger window. We could look at our table and confirm those values, and so on. So let's move on to this equation here. Same principle, we want to evaluate this, now substituting in your various values for x in this equation. Notice that we are going to need to square first to follow order of operations, which would give us 9, and -5 minus 9 is -14. We continue on in this way, substituting in for x, each one of these x values. This would be -5 minus +4, because we have to do that squaring first, which would give us -9, and so on. A couple of these are off the edge of the map. These -14s don't appear, but we just plot the points that we can and connect the dots. -2, -9, -1, -6, and so on. We want to connect these smoothly because we see that the slopes are changing, so this is going to be a nonlinear curve. And we note that these points that we're shading on this curve, everything in between, not just the points that we evaluated. If we had evaluated 1/2, we would get something in here. If we had evaluated, something between 1 and 2, we'd get something in here. So all of the points that we draw are points that would satisfy this equation. There's an infinite number of points that make this statement true, a given y point for every given x point. Okay, here we have a cubic equation. We have x to the 3rd power. That's going to mean multiplying x by itself 3 times. And these are definitely going to be right off the edge of the map here. There's not going to be much we can do. -3 to the 3rd. Remember, we're dealing with a negative here. So -3 times -3 is +9, but times another -3 is -27. And if I add 4 to that, I get -23. Likewise, this is -8 plus 4 is -4, and so on. Now, some of these points are going to be right off the edge of the map, but let's plug in what we can here. -2, -4, -1, 3, 0, 4, and so on. Let's try to complete the picture we have here. We can see this is going to need to get very much steeply negative, and this is then going to shoot up on the other side to something around 12. So trying to complete that picture, we get the following graph. Cubes generally have this kind of sigmoidal shape. This should probably be a little bit flatter here, but that's okay. Let's take a look at something like Desmos to do that. X to the 3rd. Here we have a more characteristic shape. Notice how it flattens out there, despite my poor artistic rendering. +4, we'll shift our graph up by 4. And let's zoom out so we can see this a little bit more clearly. So here we have something in the 10 by 10 window, like what we have on our graph. And you can see that it goes off past the edge of the map to values that were predicted by the table. It has this effect of falling on the left-hand side and rising on the right. It is still symmetric with regard to the y-axis because we haven't moved left or right at all, but we'll talk a bit more about that when we talk about transformations of functions. So here we have a different question. We have a question about a property of the graph, the x and y intercepts. As you may recall, the x and y intercepts are where this graph is going to hit the x and y axis respectively. We can see just visually that it hits the x-axis here and it hits the y-axis here. Now, this point is the point -2, 0, and this point is the point 0, -2. But every x-intercept is going to have a y value of 0. The x-axis is also the line y equals 0. And likewise, the y-axis is the line x equals 0. X is equal to 0 all up and down this line. And so we'll always have a 0 in this position. And therefore, it's pretty common when we say, what is the x-intercept, to not mention that this is the point -2, 0, but simply to say -2. It's technically correct to say it's the point minus 2, 0, but since it's always y value 0 when we're dealing with an x-intercept, we sometimes omit that and just say minus 2. Likewise, with the y-intercept, we would also call this minus 2, even though it is technically the point 0, minus 2. Number 9 is also asking for the x and y-intercepts. Let's mark them visually. Here are our x-intercepts, and here is our y-intercept. These are the points minus 4, minus 1 for an x value, and of course 0 for both of them for their y values. So we usually say that the x-intercepts will omit that y value of 0 and say that it has x-intercepts at minus 4 and minus 1. So this is x-intercepts, really. And y-intercepts at positive 4, where it hits the y-axis. Sometimes we have more than one intercept, as in the last problem. Here we can see one where we lack an intercept. And in generally, there might be no intercepts to an equation. For example, 1 over x, if you took a look at that graph, has no intercepts, either x or y. This one, though, we have an x-intercept. It's right here. Our x-intercept in this case will be minus 1. But our y-intercept, there isn't one, right? So you could think of that as DNE, right? Does not exist. I also enjoy the null symbol. This is not 0, of course. This means the empty set. This is null or no answers. And we want to distinguish that from the number 0 because a curve, especially one that, say, for example, intersected at the origin, would have a 0 for an x-intercept. We want to distinguish this. This is not 0, right? That's not what it means. It means no answer, that there is no y-intercept in this case. So here we have something that starts to broach into word problems, right? We have y is 3 more than 2 times the x value, and we want to write that as an equation. So y is 3 more than something. That means we're going to take that something and add 3 to it. What are we adding 3 to? 2 times the x value. And we're told that this is what y is. And so we have our equation. To fill out the table, we simply plug in x into that equation and evaluate. And we want to do that for each and every one of these as such. We then plot those points and connect the dots, extending the line appropriately. And we notice that as predicted by, say, slope-intercept form, we have a y-intercept of 3 and a slope over 1 up 2, a slope of 2. All right, that's it for this section and this video. Thank you very much for your patience. Have a great day and good luck with your studies. I'll see you in the next one.